So let's just have a look at page 11 of your worksheet. This is November 2019 P41. Okay, so state what is meant by photoelectric effect is the first definition from your notes. The emission of electrons from the surface of a metal when it's exposed to electromagnetic radiation or sufficiently high frequency. Okay. Keyword here is EM radiation or sufficiently high frequency and emission of electrons. Okay, those are the two keywords to use. And then you now look at B. One wavelength of EM radiation emitted from mercury vapor lamp is 436 nanometer. Calculate the photon energy corresponding to this particular wavelength. So we know E is equals to HF or E is equals to Hc over lambda. So since you're given wavelength here, you will use the second one. All right. So sub in the relevant values. H is your Planck constant. You get it from your data sheet on the second page of your exam paper. Because it's EM radiation, it must be moving at the speed of light. So it's 3 times 10 power 8. And after that, when you're talking about your wavelength, just remember to change it to meter from nano. So your final answer would be 4.56 times 10 power minus 19 joules. Just like that. Okay. So this one, no issues. Okay, then you move on to part B. All right. So for part B, right now what they say is that light from lamp B is incident separately on the surfaces of cesium and tungsten metal. Okay, so data for the work function energies of cesium and tungsten metal are given here. Okay, so right now they want you to calculate the threshold wavelength for photoelectric emission from cesium and from tungsten. Part 2 is asking you to calculate the work function energy for, it's asking you to calculate the threshold wavelength for cesium and tungsten. Okay. So if you recall what I mentioned to you just now, at F naught or lambda naught, HF naught will be equals to work function energy. Hc over lambda naught will also be equals to work function energy. Okay, so right now, if you want to find out the threshold wavelength for photoelectric emission, you again use the second equation. Okay, because they want wavelength now, not frequency. Okay, so the work function energy respectively is given to you. So you just use whatever is given there. You use Hc over lambda naught equals to 5. Lambda naught is Hc over 5. So you sub in your relevant values. Sub in the value for H. Sub in with the value for C. And one thing to note is that you are having your work function energy in EV. So 1 EV is 1.6 times 10 power minus 19 joules. You learned this in electric field chapter before this, okay? So EV is actually another unit of energy. So make sure you convert it to joules by multiplying by 1.6 times 10 power minus 19. Eventually, you will get this answer, 8.88 times 10 power minus 7 meter. You want to convert it to nanometer, you divide by 10 power minus 9. So that you get 888 nanometer. Okay, so this is the threshold wavelength for cesium. And if you try to repeat your calculation for tungsten, lambda naught is Hc over 5. Again, sub in your relevant values. Eventually, you will get your threshold wavelength as 276 nanometer. Okay, so these are the respective wavelengths for photoelectric emission. So let me just try and write something out here first. So just now, your wavelength for cesium was 880 nanometer. The threshold wavelength for tungsten is 276 nanometer. Okay, now move on to part D. They are asking you to use the answers in part C that you just did to state and explain whether the radiation from mercury lamp of wavelength 436 nanometer will give rise to photoelectric emission for each of these metals. So right now, if you imagine this right now, you had your mercury vapor lamp. Maybe I should just zoom out a little. Okay, you had two metals just now. Let's represent it as this one and this one. Okay, so cesium is this one, and its threshold wavelength is 888 nanometer. Tungsten is this one, and its threshold wavelength is 276 nanometer. Okay, so what you know is that any lambda less than this, okay, any wavelength less than threshold wavelength causes photoelectric emission. Okay, so remember just how I told you in your notes, threshold wavelength is the maximum wavelength to cause photoelectric emission. So because it's maximum, you cannot go more than that. You need to go below that. That's the reason why it's called maximum. Okay, any wavelength less than that maximum ought to be able to give you your photoelectric emission. So right now, that's what you're trying to do here. They already told you that your mercury lamp has wavelength of 436 nanometer. So you imagine right now, if this one is your mercury lamp, this one is your mercury lamp, is emitting EM radiation whose wavelength is 436 nanometer right now. Okay, so you want to evaluate whether this wavelength is going to cause photoelectric emission for cesium or tungsten. Okay, so right now what you can say is that if you're talking about cesium itself, the wavelength of the photon emitted by your mercury vapor lamp is actually less than your threshold wavelength. It's 436 nanometer compared with 819 nanometer. Okay, so because it's less than your threshold wavelength, therefore you're going to have photoelectric emission. Okay, so this one here, you can actually say there is photoelectric emission since 436 nanometer is less than 890. But when you go to tungsten, the wavelength of the photon emitted by a mercury vapor lamp is actually greater than the threshold wavelength, because you see it's 436 compared with 276. So you are not going to have any photoelectric emission. This one will not give you anything. Okay, so that's just one thing to take note of for this particular question. So this is okay. Then you move on to a next question. Next question that you can do is actually page 26. Okay, so you're okay, I'll move on to that. Page 26 is actually this one. Okay, it's June 18 P42. So I'll clear this one up. Okay, so describe photoelectric effect is the same question that we did earlier. Is emission of electrons from surface of a metal when EM radiation of sufficiently high frequency is incident on the surface? Just copy the definition from the notes and you should be fine. Now, if you look at part B here, or page 26, data for work function energy 5 for two metals is as shown. You have sodium, you have zinc. Light of wavelength 420 nanometer is incident on the surface of each of these metals. Now, state what is meant by a photon. A photon is just simply a packet of energy of electromagnetic radiation. If you say it's a packet of energy, it's 1 mark. If you say it's EM radiation, it's another mark. Okay? But in your marking scheme, they can also word it differently, not just packet of energy electromagnetic radiation. They can either just call it a quantum of energy or electromagnetic radiation, or discrete amount of energy of electromagnetic radiation. Okay? Anyone would be acceptable. So for your next part, they ask you to calculate out the energy of a photon of the incident light. So since they gave you information on wavelength, you just use E equals to hc over lambda. So Planck constant value, get it from the datasheet, use speed of light, divide by your wavelength, change to meter, you will get your answer as 4.74 times 10 power minus 19 joules. Okay, so this is pretty straightforward. And now, if you look at your last part of the question here, they are asking you to state whether photoelectric emission will occur for each of these metals. Okay. Now, if you recall what I mentioned to you earlier, work function energy phi is actually the minimum in energy required to remove an electron from the metal surface. Okay. If your energy of your photon is actually more than your work function, you will have photoelectric emission. But conversely, if your photon energy is less than your phi, you will have no photoelectric emission. So right now, if you look at your work function energies that has been given to you from your question, phi for sodium is 3.8 times 10 power minus 19 joules. Whereas the energy of your photon incident on the sodium is 4.74 times 10 power minus 19. So right now, you can see that E is actually more than the work function energy of sodium. 4.74 is definitely larger than 3.8, right? So you're going to have photoelectric emission. But now if you look at zinc, zinc is 5.8 times 10 power 19 minus 19. Your energy of photon is 4.74 times 10 power minus 19. If you compare 5.8 and 4.74, obviously your energy now is less than your work function energy. Therefore, you are not going to have any photoelectric emission. Okay, so that is one other part here to take note of. Okay, so your questions, when they ask you whether you're going to have photoelectric emission or not, they sometimes may ask you to base it on your threshold wavelength. Sometimes they may ask you to base it on your threshold frequency, and some other cases they may ask you to base it from your work function. Okay, so you need to learn how to evaluate each case accordingly. So page 26 is done. If you're okay, then we move on to page 19. Okay. Right, so let me clear this thing off. Next question that you can have a look at is actually on the page 19. So have a look at page 19. Page 19, this one is June 17 P42. All right. So briefly describe two phenomena associated with photoelectric effect that cannot be explained using wave theory of light. Okay, so just now in the first page of the notes, I already told you that the wave theory of light cannot be used to explain photoelectric effect. There are 4 observations that actually tells you that. That one is actually listed right over here, bolded in yellow here. So any 4 of these would actually be suitable. Okay, just pick either one. Instantaneous emission of electrons, existence of minimum frequency to cause photoelectric emission, maximum CAIE of photoelectrons is independent of intensity of EM radiation but increases with frequency of EM radiation. If there's anything I need to ask you to be cautious of is the last 2. Please make sure you always write maximum CAIE. Okay, if you don't write maximum KE, but you just say KE of photoelectrons is independent of intensity, KE of electrons is increasing with frequency, most of the time it won't be accepted. Okay, you must use the term maximum KE. Okay, maximum KE here is an important phrase to use as your answer. Okay, so now if you look at your questions, minimum frequency for emission of electrons from the metal surface, that's 1. Maximum Ka of electrons is emitted is independent of the intensity of your EM radiation, that is 2. And then after that, what other things to say? Yeah, instantaneous emission of electrons, and that maximum energy of electrons depends on the frequency, or maximum Ke lah, if you wanted to. Okay, so any one of those form the notes. Now, if you then move on to B, the maximum energy Emax of electrons emitted from a metal surface when illuminated by light of wavelength lambda is given by this expression, where Emax is Hc times 1 over lambda minus 1 over lambda naught, where H is the Planck constant and C is the speed of light. So identify here the symbol lambda naught. So this symbol lambda naught is actually your threshold wavelength, maximum wavelength for photoelectric emission. Okay, you just need to state what the symbol means. Okay, you don't need to explain what it actually is. Okay, then after that, before I go any further, your Emax here is actually referring to your Ke max. Okay, although they didn't say it's kinetic energy, they just say it's maximum energy. It's already understood it's Ke max. Okay, if you look at this equation here, it seems different from the ones that you had in the notes previously. It's actually derived from that same equation. If you say that HF is equals to Ke max plus phi, I change it to wavelength form. This one is Hc over lambda equals to Ke max plus phi. Okay, so if you recall that I mentioned to you that Hc over lambda naught is equals to phi, you sub it inside here, what you will get is Hc over lambda equals to Ke max plus with Hc over lambda naught, such that right now Ke max is going to be Hc over lambda minus Hc over lambda naught. Factorize out your Hc, you're going to get 1 over lambda minus 1 over lambda naught. So right now, this is your equation, which is actually this one here. Okay, so it's actually the same equation from photoelectric equation. So right now, if you move on to the next part of your question, they told you that the variation of 1 over lambda of Emax with metal surface is as shown in figure 10.1. Use the figure to determine the magnitude of lambda naught. Okay, so your original line on your diagram was this one. Okay, this is a graph of Emax or Kmax versus 1 over lambda. So just now earlier I mentioned to you this equation here, if you rearrange it, it will be Ke max equals to Hc over lambda minus with Hc over lambda naught. So this one here, I can further rewrite this as Hc 1 over lambda minus Hc over lambda naught. When now I compare it with your straight line equation, y equals to mx plus c. So here you can already say that y-axis should be my Ke max, x-axis should be 1 over lambda, which is exactly what you're having right over here. Okay, so from there you can conclude that your gradient is going to be HC. Okay, so let me just rewrite this. Your gradient is actually your HC, and your y-intercept is going to be negative HC over lambda naught. Okay, so right now they want you to determine the magnitude of lambda naught. If you recall what I also mentioned to you that time, if you try to draw a graph of KE max versus 1 over lambda, you're supposed to get a straight line graph with y-intercept. So this part here is your negative phi, negative work function. This one here, the x-intercept is your 1 over lambda naught. Okay, it's 1 over lambda naught because your axis is 1 over lambda. Okay, you get lambda naught when your KE value is 0. Okay, remember what I said just now? So what you just need to do is that existing line that you have in your graph, just draw another separate line following the original line. Extrapolate that line until it hits your x-axis. And then read off the value of the x-axis here. That value, 2.2, is equals to 1 over lambda naught. So here you can say that 1 over lambda naught is 2.2 times 10 power 6 per meter. Just find out your lambda naught is 4.55 times 10 power minus 7 meter. Okay, so that one should be pretty straightforward for you. Okay, then next part. Let me clear this thing off because it's in the way. Okay, so for the next part, use the gradient of the figure to determine a value for the Planck constant h. So based on what we've already just done earlier, you already know that your gradient is going to be hc, right, based on this alone. So hc is equals to your gradient. Just pick any 2 points on your graph and find out the gradient. Okay, so in your case, you can just write this hc is equals to gradient. So pick any 2 points on your graph, find out the value of the gradient, and then after that, what you do is you sub in the value of your speed of light to find out your h after that. Okay, so here is your working. H is equals to speed of light. H times speed of light equals to this value of gradient. Your h eventually would be 6.67 times 10 power minus 34 joule second. Okay, right? So pretty straightforward in your case. Okay, so if this is okay, then you move on to the very last part of your question. Okay, the very last part of your question mentions this. Let me just read it out. They say that the metal surface in B is now oxidized. Photoelectric emission is still occurring, is still observed, but the work function energy has increased. So on figure 10.1, right over here, draw a line to show the variation of 1 over lambda of E max for the oxidized surface. Okay. So right now, if you think about it, if you recall the original equation for your photoelectric emission, the photoelectric equation, which was this one, I show you that you can derive it into this form and equate it to a straight line equation where subsequently you will get a straight line graph with a negative y-intercept. So right now, they told you that for the oxidized surface, maybe I'm just going to write it here. They tell you for the oxidized surface, phi has increased. Okay, your work function has increased. That's what they say. The work function has increased. Okay, so if you look at the original diagram just now, let's just say that this one was the unoxidized surface, your phi has increased, work function has increased. You can actually say that your y-intercept is more negative because magnitude has increased. Because magnitude of lambda has increased. Okay, that's number one. Magnitude of phi has increased. Okay, because originally you already know that y-intercept is negative phi, right? So if say for example my work function was, say for example when it was unoxidized, it was 1.2 eV. When it's not oxidized, it could probably be 3.6 eV now. It's supposed to be lower now when I translate it into my y-intercept because the magnitude is larger. Okay, so if I look at this original graph that I have, I would have a y-intercept that is lower. Let's just say right around here. Okay, so I should expect a straight line again from there, which is lower now. That straight line that you draw must still be parallel with the original line, because what you could say was this also, because if you recall, what is your gradient? Your gradient is actually h times c, isn't it? Your Planck constant is a constant, your speed of light is a constant. So since both of these variables is constant, therefore your gradient should remain constant. Okay, so here another thing that you could also take note of is that the gradient of line remains the same, since gradient is equals to hc, the product of two constants. Okay, so you should still get a line with the same gradient as before. It should be parallel. Okay, so like right now, if you want to draw, you could probably draw something like this. Okay, just make sure it is parallel to the original one. But yeah, there's another thing to this question also. How do you know that your x-intercept is going to be 2.5? You'll notice here that I draw a line that is parallel to the original one and is lower. But why is it that I draw it specifically at 2.5? Okay, there is a reason for it, I believe. Do I have a reason for it to draw it at negative 2.5? Oh, this one is no. There's no particular reason why I drew it at 3.5. Okay, no particular reason. That one is more for a different question, because I don't have enough information here to find out the new threshold wavelength. Okay, so you can just draw it at anywhere you want. Okay, it can be at 2.5, it can be at here, it can be at here, anywhere, any x-intercept you want. Okay, right? But just make sure that once you've chosen a value there, make sure that you draw your line parallel. Like in my case, probably the only reason why I chose this is because I can see that there's a nice 5 units of boxes here. Sorry, this is not 5 units. The only reason why I chose is because 2.5 is a nice value there. So right now, what I could see is that this one is around 6 boxes, 6 small boxes. So this one here, you can see that there's 6 small boxes. When I want to draw a line parallel to it, how do I ensure that the line is parallel? If you already identify one point here that is 6 boxes away from the original line, you just need to choose another point that is 6 boxes away. Let's just say on your original line right now, I pick this point. I know that the new line that I draw must also be 6 boxes away, because the first one here was 6 boxes, the next other one must also be 6 boxes. So if you have these 2 points defined here, you can easily draw your parallel line. Okay, that's the easiest way to draw a parallel line. Just pick 2 points, offset it by the same amount. Okay, so maybe I just write it here. To draw parallel line, pick 2 points and offset by the same amount, like what I just did here. Okay, so that one should be for this particular question. Okay, so if you just have a look at page 5 of your worksheet, this one is November 15 P41. So for this particular question here that you have, by reference to the photoelectric effects, that what is meant by the threshold frequency. So we already learned this just now earlier. The threshold frequency is just simply the minimum frequency of electromagnetic radiation for emission of electrons from a metal surface. That's all there is to it. And now in B, you have electrons are emitted from a metal surface when light of a particular wavelength is incident on the surface. So explain why emitted electrons have a range of values or KE below a maximum value. So this one was also kind of explained to you just now already. If you consider a metal surface right now where you have many electrons below that surface, like the ones that you're having right over here, like this, it is only the electrons near the surface that have max KE, whereas the electrons deeper below the metal surface would have less than max KE. So what I mentioned to you then was that the deeper the electrons, the more work has to be done. The more work has to be done to bring to surface and escape. To bring to surface and escape. So to bring to surface and escape. And then after that, what will happen is that the less energy to be converted to KE. The less energy remaining to be converted to KE. That was the basics of what I just mentioned to you. Okay, so only electrons at the surface will have maximum KE, but the electrons deeper below the surface will tend to have less than max KE. Because what I mentioned was that the deeper the electrons are, the more work has to be done to bring to the surface because it's trying to overcome all the attractive forces between the nuclei. So as a result of that, you actually would have less energy remaining to be converted to KE. So how you want to translate it as your answer here, you write something like this. Electrons at the metal surface are emitted with maximum KE. Only electrons at the max. Maybe it's better if I just add something here. You can probably just say this. Only electrons at metal surface are emitted with maximum KE. For electrons below the metal surface, they are actually emitted with less than maximum KE because energy is required to bring them to the surface. This will explain why you would have a range of KE values. Okay. Now, then if you look at C, the wavelength of the incident radiation is lambda here, and the variation is 1 over lambda of maximum KE Emax of electrons emitted from the metal surface is as shown in the figure below. This is the same KE max versus 1 over lambda line that we had from before. So here, in this particular question, use that figure to determine without reference to work function energy, your threshold frequency F0. Okay, so here you want to find out what is your threshold frequency, but you're given a K max versus 1 over lambda graph. So if you're looking back at the same photoelectric equation from before, this one, let me just try and rewrite it out for you. Ke max would be Hc over lambda minus phi KE max would be HC 1 over lambda minus 5, so that eventually your graph looks like this. So let me just write it out. This is what you are expecting right now from your graph, or K max versus 1 over lambda, which is what you are seeing in the actual question itself, just that they didn't draw the full line for you. So here, they want you to find out the work function energy. They ask you to find out the threshold frequency without referring to the work function energy. Okay, so how are you going to find that out? What you do know is that this part here must be 1 over lambda naught, whereas this part here must be negative work function. So they already told you specifically, don't use work function energy. Don't use any equation related to work function energy here. Meaning to say you don't use HC over lambda naught equals to phi. You don't use HF naught equals to phi. Because they told you do not use that without reference to the work function energy. So you cannot use this now. So how are you going to find the threshold frequency then? So what you first do is you read off the threshold wavelength from your x-axis. So what you can find now is that your 1 over lambda naught is 1.85 times 10 power 6. The graph that you have is incomplete. You have to extrapolate a line to reach the x-axis. Okay, this was your original line over here. Just extrapolate the line so that it touches your x-axis. This 1 over lambda naught is 1 over lambda because the axis is 1 over lambda. So this 1 over lambda naught is 1.85 times 10 power 6. Okay. So from there, what you can do further is to relate it to frequency then. Because if you recall your equation for wave, this was the common equation that you have used before. If I change it to take into account speed of EM radiation is C equals to F lambda. So your F would be equals to C over lambda. If this one is F naught for frequency, your lambda must be F naught. So you want to use this equation. Okay. So right now, if you already found out what is 1 over lambda naught as 1.85 times 10 power 6, what you can then do is to say that F naught equals to C over lambda naught, which is C multiplied with 1 over lambda naught. You just need to substitute the value that you have earlier into here and submit the value of your speed of light, and you'll be able to get the answer as 5.55 times 10 power 14 hertz. Okay, this is the working here. Okay, I think there are certain things here in my original writing that is actually unnecessary. So I'll just circle the things that you can write. You can write this one. You can actually also write this one already. Okay, so all these things that I circle in blue here is actually something you can just write. The ones before this, you don't need to write this now. All right. Okay, so you already found out what is your threshold frequency. From there, the next part of your question is where they want you to find your work function energy. They didn't want you to use anything related to work function energy in the previous question. Now this question, they want you to find the work function energy. So you know that the relation between threshold frequency and work function energy is actually just HF naught equals to phi. So phi is just you taking the Planck constant, multiplying with your threshold frequency, giving you 3.68 times 10 power minus 19 joules. Okay, so this one is pretty straightforward. Okay, so if then it's okay, then you move on to part D here. Okay, so for part D, just give me a moment while I erase off all those unnecessary stuff. Now for part D, they told you that cesium metal has work function energy of 2.2 times 10 power minus 19 joules. On the axis of the same figure, sketch a graph to show the variation of 1 over lambda of Emax for cesium metal. Okay, so right now, what you have here is some unknown metal. They never told you what was your original metal. But did they tell you that your original metal, the work function for the original metal is 3.68 times 10 power minus 19 joules. This is what you found above here. Okay, this is the work function energy of your original metal. Now they told you that now you have another metal, cesium. So the work function energy of cesium is specifically 2.2 times 10 power minus 19 joules. You want to sketch a graph to show the variation with 1 over lambda of Emax for cesium metal. Okay, so you know by right, it should still follow this equation because it's photoelectric emission. It should still follow photoelectric equation over here, such that if you were to plot a graph of K max versus 1 over lambda, you should get a straight line graph with a negative y-intercept. Okay, so that's the idea here. But there are a few things to note from there. All right. So here, in your case, let me just write something here. If you compare between the original work function and the cesium work function, the work function of cesium is actually less, right? So therefore, your y-intercept is higher on the graph. Or what should I say? The y-intercept is less negative now, following what I mentioned just now. Y-intercept is less negative. Okay, so your graph line is shifted higher. That would mean. So this one, therefore, graph line is shifted higher. Okay, because from here I know that from this original equation, gradient is equals to hc, y-intercept is equals to negative work function. So right now, if my work function is less than the original one, my y-intercept is less negative, so the graph line must be shifted higher. Okay, that's one part here. So another thing here that I can also kind of say is this. This one is number 1 now. So number 2 will be gradient is equals to hc, product of two constants. Therefore, gradient of line remains the same. Okay, that one is one thing I should have. So now, that new line that I draw would be higher, like this, in this manner. Okay, so this one is what I expect to see. A less negative work function, and then a gradient that is still the same as before. Okay, now here, when you're talking about your x-intercept, this one, you need to be specific on what is your x-intercept value here now. Just now I tried to find the value of x-intercept for the previous question, but I didn't manage to because I don't have enough information. I say you can just pick any x-intercept you want. But for this question here, you cannot just simply pick any x-intercept you want because they've already given you your work function energy here. So before you start drawing your graph, there is a higher one than the one before with the same gradient. You also need to first set up what is your x-intercept. So this one is where you need to start finding out what's the value of your x-intercept. So if you recall that hc over lambda naught is equals to work function, 1 over lambda naught will be equals to pi over hc. So that right now, if you take the work function of the cesium metal, 2.2 times 10 power minus 19, you divide it with the product of Planck constant, 6.63 times 10 power minus 34, divided by the speed of light, you are going to get 1 over lambda naught as 1.11 times 10 power 6 per meter. So when you draw your when you draw your line, make sure that it hits an x-intercept of 1.11 on your graph. 1.11 times 10 power 6 on your graph. Okay, make sure it hits the x-intercept at 1.11 times 10 power 6 on your graph. So now, if you want to draw your graph, it should be like this now. Okay, so let me just erase off some of the unnecessary stuff. So this one was your original line. Okay. Now, when you draw your other line, I mentioned to you, it must be shifted higher because there's a less negative y-intercept. It must be drawn with the same gradient. And now, when you draw it out, please make sure it hits 1.11. Okay, there's a reason why you need it to hit this point here, because this is 1.1. Okay, you just found out what is the value of your 1 over lambda naught. Okay, so here, once you already set that point there, if you want to proceed with drawing a parallel line, just like I mentioned to you, to draw your parallel line, so that you have a line with same gradient, to draw parallel line, pick 2 points and offset by same amount. Since you already have this first point here, you look at your original line, how much is this in terms of the number of small boxes? So you go and pick another line, another point on the original line, maybe this one. You again offset it by the same amount so that you get 2 points here. So from there, all you just need to do is you just join those 2 points, you will get the required line already. Okay? So that's how you would generally do this particular question, which is about 2 marks. Okay? It's still the same 2 marks as the previous question, but it requires a bit more work.